Okay, now we are going to take steps to specialize our complete markets model with trading of a complete set of one period arrow securities. We're going to specialize it in the direction of Bellmanizing it. So we're going to accomplish this by making a restriction on putting a restriction on the stochastic process that governs the distribution of ST belonging to S. Okay, so just to review before, for all t greater than or equal to 0, we specified just an arbitrary joint probability distribution over histories ST. And we did a lot of work with what we called conditional densities. These played a big role for some tau greater than or equal to t. These played a great role in our formulation, and in particular this one that we wrote down played a big role in our formula for the one period arrow securities price. And the annoying thing was there's so many histories, and our arrow security prices were indexed by these histories at each t. And this was an implication of our setup where we had joint probability distributions that looked like this, and we specified, in general, we allowed YT I for a particular person, the endowment for a particular person to depend on the entire history. Okay, so we got pricing kernels that also depended on entire histories. And furthermore, we got a distribution of wealth. Could write this like this. That was the wealth or the asset holdings of person I at date t after history. These all depended on the entire history. Okay, so we're now in the business of Bellmanizing things, and the way we're going to do that, see, in order to reduce as a prerequisite of that, we want to reduce dimensionality. And this is a key step in reducing the number. We want to reduce the number of objects we have to keep track of in order to formulate our theory. And for applications, that is essential. So we want to limit the number of state variables. Okay, so the way we're going to do that, so here's the key steps. The key step is we're going to assume that pi t of ST is generated by a Markov chain. That's what we're going to do from now on. And we're going to write this probability ST plus 1 equals S prime, condition on ST equals S. We're just going to let that now be pi of S prime condition on S. So this is our transition kernel or transition matrix or transition function. Okay, so now we're going to get this specialization. We can, well, this, you know, we can always do this. You can always do this. Oops. You can always just use the, without the Markov property, we can do this. With our initial. But now, with the Markov property, we can replace this with and this is the key step. So we're going to now assume Markov. So this is going to imply, if we now just go back and rework or revisit what we had with our competitive equilibrium with trading of euro securities, we're going to see this is going to this is going to simplify things. So this is going to imply a bunch of simplifications. And first thing is YT, we're going to make YT, this is going to be an assumption. We're going to assume that YTI is a function only of the Markov state. So the endowment of person I only depends on the on ST, not on the history. So we're going to assume from now on. So what this is going to imply is that equilibrium allocations immediately follows from what we've done before, that equilibrium allocations are now, they're now just going to be a function only of the current Markov state. They're not depend on the history. See, before they could depend on the history in a restricted way that we spent a lot of time talking about. They depended before, they depended only on the aggregate endowment, which could depend on the history, but that itself was reducing they depended only on the history to the extent that it influenced the aggregate endowment. We spent some time talking about that. Two histories that led to the same aggregate endowment produced the same allocation. But now, with the Markov property, they only depend on the current state. It's also true, of course, so like an exercise, if two current Markov states lead to the same aggregate endowment, they're also going to lead to the same allocation. You could check that out. Another thing that we automatically get is we're going to get our pricing kernel, one step ahead pricing kernel. This is now going to just be, going to be replaced by, instead of depending on the entire history, this is now just going to depend on the Markov state. That's going to be a benefit. And we get a nifty formula for it, which is used all over finance and macro. I'll even take the twiddle off. It's going to be this. It's beta U prime for any individual again for any individual times now the one-step Markov transition probability. So this is our formula. This object is an example of what's called a stochastic discount factor. We'll spend more time talking about that. Stochastic discount factor. One step. Okay, more things are going to be true. Further implications are we're going to have that this key object in the arrow securities, the debt limits, are going to be a time invariant function of the Markov state. And here I want to point something out that's really significant. There's no time subscript here. This is going to be the same function for all t. So what we did have before in a general context, we had a different function because we had to keep track of histories for all t, but now we just have a single function for the Markov state. That is a huge simplification. So this is the these are the debt limits. Now you might ask, well, wait a minute. Stare at this right here, up above, and the same thing is true. There's some t's I can erase. And by the way, I wrote this wrong. This was, should erase this. This was, let's go back. This was QT. That's the one-step pricing kernel in the general trading with arrow securities. There was a T here because this is the price at time T. And this now just depends on not on the history, but on ST. And now what I can do is I can erase, there's no T here. This is going to be time invariant. So this is going to be a time invariant function of the Markov state, and we can check that out right here. This is just going to be a function of, I'm going to lower this now. It's really important to keep in track of this, and there's no T here. So this is a time invariant, one step ahead pricing kernel. And how did I get away from eliminating the T? Well, there's no T in these functions. There's no T here. There's no T here. Oh, there's a T here. But you could say, didn't you just tell me there was a time invariant transition? So there's actually no T here. So what we've eliminated is all these, we've got time invariant pricing function. It depends on, if you're in this state, ST today, this is what you pay for 1 unit of consumption tomorrow if state ST plus 1 prevails. Okay, so the similar logic is going to imply that we don't need a T for the A's. What are the A's? These are borrowing limits. These are Markov state by Markov state borrowing limits, and we need those. And then another thing that's going to be true is you might have guessed this, when we compute the continuation wealths, which were an object in the general setting with arrow securities without Markov ST processes. This is just going to become simplified to no T. This was a T here. There's no T. And this is just going to be of ST. So this was a time invariant continuation wealth. So what we've done by specifying a Markov ST process is we've eliminated lots of time dependence. And statisticians and econometricians like that because we've far reduced the number of parameters. Instead of having a separate function here for every T with an increasing number of arguments, we've both, in one fell swoop, we've both reduced the number of arguments. Instead of keeping track of the history, we're just keeping track of today's Markov state, and we only need one function, holds for all time. So, if we take the phrase that Arthur Goldberger said and Lucas loved, beware of theorists bearing free parameters. We've taken that to heart. Okay, so now we are ready to Bellmanize the competitive equilibrium with arrow securities. Okay. So here goes. We're going to, so when you do dynamic programming, you always begin with one word, and that word is let. Okay, so let's do it. Let V I A S be the optimum problem, the optimum value for a consumer I who has, I could say, wealth or assets A and Markov state S. And who, I can be verbose now, can trade one period arrow securities at prices Q S prime given S. It's going to be the optimum value function. And this is going to satisfy, so I have to write max, and then below I have to say what the person chooses. Person chooses consumption and chooses a portfolio, which I'll just say, we'll call this A hat of SI, AI of S prime. Prime means next period value. So this is a vector. This is a vector. That's a scalar. UI, because it might be my own utility function of C. That's my consumption today, plus beta. And now I just have to, tomorrow, I sum over tomorrow's state. I do VI. Now when I get to tomorrow, I'm going to be at, I will have wealth A prime of A hat of S prime, and I'll be there tomorrow. But I'm going to transit states. So that's my Bellman equation. It's my value function tomorrow at tomorrow's wealth, tomorrow's state. That's the expected value. And now I have to have subject to some constraints. Well, we're going to pose C is greater than or equal to 0. Some sense our Arnott condition is going to do that for us. And now I have to include my no Ponzi scheme constraints. So I can't borrow more than the there's a collection. There's as many of these constraints. These are my debt limit constraints. You have to have these constraints. Okay, so Not quite done. Consumption has to be positive. My debt limit constraints. And now I have my budget constraint. So consumption plus what I consume and then what I buy in my portfolio. So this is my purchases. These are my portfolio decisions. I'm buying wealth next period in state S prime. And these are my prices, my kernel. And this has to be less than or equal to, well, my income today in this Markov state is this. I've expressed this as a time invariant function. That's what we did before above. And then plus, here's my current wealth. So that's here's my Bellman equation, and here are my constraints. This is a budget constraint, trading with euro securities. This is a no borrowing constraint, and I'm imposing that consumption is positive, not negative. Okay, step at a time, we're getting there. We're creeping up on something beautiful. Well, so the optimizers, the optimum decision rules, what are they going to look like? Well, they're going to have this form. Consumption is going to be a function of, this is what used all over macro, wealth, NS. This is an equation that central banks think about all the time, because they're concerned about consumption and they're concerned about the wealth, people's wealth and the quote unquote wealth effect. And then portfolio choice is going to look like this. It's going to be a set of functions. It's going to map my current assets, my wealth level, the current state, and it's going to be a function that looks like this, AS, and then it's going to tell me what S prime is. Guess I don't even have to, yeah, I'm going to write it like that. Just to indicate that there's going to be, because I want it to be a function, there's going to be one of these for each S prime. Okay, now we're ready to define an equilibrium. We want to define we're going to call it a recursive competitive equilibrium with trading of one period euro securities. We're going to define that. Okay, so let's have a definition. So remember, our definitions are, they're going to be a blank is a bunch of stuff that satisfies a bunch of conditions. That's what our definition is going to look like. So we have to fill in the holes. So definition. We have to fill in the blanks. A recursive competitive equilibrium okay, is an initial distribution of wealth. So that's going to be a vector across all people. I'll write it like that. A set of borrowing limits it's going to look like this. We'll call them A bar I of S. Now we've really cut down the number of these, and I is going to go from 1 to I. As many people we have, as many different people we have, if we count these, we have how many of these are there? There's going to be I times the dimension of S. That's how many borrowing limits are we going to have. A pricing kernel it's a pricing kernel, Q of S prime given S. We're going to have a set, we're going to have sets of value functions. They're going to, what do these look like? These are VI A of S. They go from I equals 1 through I. And decision rules HI A of S, GI, that's my portfolio. A S S prime goes from I equals 1 through I. Bunch of things. Such that, okay. So here we go. A, the state by state borrowing limits satisfy I'm going to call this the recursion, or I'm just going to say the Bellman equation. Here's another Bellman equation. AI of S equals yi of S, it's a function of the Markov state, plus summation S prime Q of S prime S A bar I of S prime. So that itself is a Bellman equation of a sort. Okay, we have to solve that. We can think about solving it later. Okay, here B, for all I, given A0I, A bar I of S. So given this and this, and the pricing kernel, and Q of S prime S. So for those given things, the value function and the decision rules solves the consumer's problem. That's for every consumer. Okay, so you notice this problem is this person's a price taker and he's a debt limit taker. And he's given an initial wealth, he or she. And C, for all okay, I'm going to write this last one in a kind of a non-recursive way. For all realizations. So now I'm kind of abandoning the recursive setup, but I want to do it nevertheless. The consumption and asset portfolios implied by the decision rules satisfy. It's got to be true that summation I, the consumptions are going to have to add up to yi of st, and summation of I, my asset portfolios. Well, I can write this. I'm going to write this like this. A hat of S prime is going to be equal to 0. For all t and all histories. Okay, so I want assets to borrowing and lending state by state to balance out next period. Where these are the objects that come from our A hat of S prime. Is equal to G of A ST S prime. That's what I plugged in there. So those are our requirements for a recursive competitive equilibrium. And I'm going to say more about C at a later moment, but not right now. Okay, so this bears stare at the above. Okay. Okay, I'm just going to make a confession and a forecast, and then give you some benevolent advice. My confession is when I make up problem sets or exam questions, or devices to help people learn, what the structure of these competitive equilibria with trading of one period error securities are. What I'll often do is I'll describe an economy, and then I'll say, and it'll have Markov endowment process for everybody. And I'll say, well, first define a competitive equilibrium with trading of one period error securities. And please tell me all the objects that comprise an equilibrium. So now you have to give me the list of things. And then I say define an equilibrium. You have to tell me the list of conditions that are satisfied. Okay. Okay, then I say, well, for this example, compute one. Compute one. And I put your focus entirely on the equilibrium with trading of one period error securities, competitive equilibrium. So here's my advice how to compute it. And it's to take, so to compute what we'll call a shorthand, a recursive competitive equilibrium with complete markets in one period error securities. To compute that, here's my advice. It's take an indirect route. And use some of the findings that we have above. So here's the steps. One, this is in compute an equilibrium, a competitive equilibrium, I'll say, a competitive equilibrium of the corresponding Arrow-Debreu economy with time zero trading. So compute that. Now, how could you compute that? Well, just wait a minute. Set, wait till you see step 2. Set the equilibrium allocation of the sequential trading, that is arrow securities, you see what I'm going to do. Economy to what you computed in step 1. Okay, now remark, you can compute equilibrium allocation here by solving a planning problem that we discussed. So you solve the planning problem for the economy starting at time 0. 3, compute equilibrium pricing formula from Q S prime given S equals beta U prime Use that formula. Well, where do you get the allocation from? You get the allocation from up here, the second step. Four, compute debt limits from the element equation that we described just a minute ago. AIS equals YIS plus beta summation S prime Q S prime given S A I S prime. Solve for AIS, a vector, for each I. Five, compute portfolios by solving another element equation. That's how we do it. So this is a lot to digest. And on section 994, there's an example, a simple example where this algorithm is used to compute a recursive competitive equilibrium. So this is this achievement of these. They're beautiful models, and they're workhorses all over macro and finance. So hope you have fun with them. Thanks.